Polya's random walkers. In this video, we will discuss the probability of a random walk returning back to its origin in 2 and 3 dimensions. Let's start with the part A, which is the two-dimensional random walk. Starting from an origin O, a particle has a 50-50 chance of moving one step north or one step south, and also a 50-50 chance of moving one step east or one step west. After the step is taken, the move is repeated from the new position and so on indefinitely. What is the chance that the particle returns to the origin? Let's first look at the solution of this two-dimensional case before moving on to the three-dimensional case. First, let's visualize the two-dimensional space that the random walk can traverse. Here, the random walk starts at point O, shown by this blue dot. Then, it can take steps to either northeast, northwest, southeast, or southwest. After that, it repeats the same kind of steps. Overall, we get a two-dimensional lattice like this. First, let me remind you that in the one-dimensional random walk case, the probability of the walker coming back to its origin was 100%. And it returned back to its origin infinitely many times. This was previously discussed in the cliffhanger problem in this channel. We call this kind of a walker a recurrent walker. So what is that probability in 2D? First, let's note that the random walk's movement in horizontal and vertical directions are independent. Imagine flipping two independent coins to determine the direction in each axis. That's why we say that the x and y direction movements are independent. Next, let's note that for the random walker to come back to its origin, both x and y should be equal to 0. Therefore, the random walk can only come back to its origin at even steps. Let's call the total number of steps to be capital N equal to 2n, where this small n can take values from 1 to infinity. To see that, let's just focus on one of the dimensions, say x. Then, out of 2n steps, n of them has to be to the right, and another n has to be to the left so that they cancel out and it ends up back at 0. Now, how many such paths are there? For example, one such path is the one where the random walk takes n consecutive steps to the right and then n consecutive steps to the left. But that's just one possible path. Overall, the degeneracy or the number of total such paths is going to be the combinatoric 2 choose n. Here we can choose either the right or the left steps. Let's call this gx. Then what is the probability that the x component of the walk is going to be 0 for a given value of n? The probability of any possible path has to be 1 over 2 to the power of 2n, since at every step it has a 50-50 chance of going in opposite directions. And then we have to multiply by the weight or the degeneracy, which was gx. Substituting gx gives us the following expression. Now, this is quite a complicated expression. And because we will have to do some summation using this expression, we need to somehow simplify it. Because the sum is going to go from 1 to infinity, we will approximate that n is much larger than 1. You will see that this approximation actually does not introduce an error in our final result for two-dimensional case. In this case, we can use the Stirling's approximation for n factorial. It says that n factorial is asymptotically square root of 2 pi n multiplied by n over e to the power of n. Substituting the approximate form of n factorial into our x component probability gives the following expression. you will see that a lot of this cancels out, leaving us 1 over square root of pi n. Now, as we said, the x and y components are independent, and also they have to be the same as they are symmetric. Therefore, to get the two-dimensional probability, we multiply the x and y components, giving 1 over pi n. Now, this probability that we just found is the probability that the random walker is at the origin at exactly 2n steps. However, we want to find the probability that it ever comes back to its origin. To do that, it's much easier to think about the mean number of walkers that come back to its origin. Note that this Pn is actually the same thing as the mean number of walkers that come back to its origin at 2n steps. To get the net mean number of walkers that come back to its origin, we need to do a summation from 1 to infinity. Plugging in mu n from the above expression gives us this summation, which is known as the harmonic series. For a particular value of n, it converges to natural logarithm n, which goes to infinity as n goes to infinity. In other words, this is a divergent series. What this means is that, on average, a particle returns to its origin infinitely many times. So the particle is again recurrent, just as in the one-dimensional case. And because it comes back to its origin infinitely many times, we can say that the probability of it ever coming back to its origin has to be 100%, or equal to 1. Alright, now let's move on to the three-dimensional case. As in the two-dimensional walk, a particle starts at an origin O in 3 space. Think of the origin as centered in a cube 2 units on a side. One move in this walk sends the particle with equal likelihood to one of the 8 corners of the cube. Thus, at every move, the particle has a 50-50 chance of moving 1 unit up or down, 1 unit east or west, and 1 unit north or south. If the walk continues forever, find the fraction of particles that return to the origin. Okay, so let's first visualize this three-dimensional random walk. It starts at the center of the cube, shown by this blue dot, and goes to one of the red dots at the corners. Now, just like the previous part, Pn can be obtained by the product of the 3 independent probabilities for x, y, and z. We found previously that for one component, it is approximately equal to 1 over square root of pi n. So the net probability is going to be approximately 1 over pi n to the power of 3 over 2. Again, remember that we can think of this as the mean number of walkers that come back to its origin at 2n steps. Now we have to sum up the mu n. But this time you can see that this is going to be a convergent series, for example using integration of this function. Therefore, because this is a convergent series, let's not use the approximate form. Instead, let's try to work with the exact formula. So let me copy the exact mu n from the above for the one-dimensional case. And it's going to be to the power of 3 of that expression. Now we take the summation of this expression from 1 to infinity. Because this is quite a complicated expression, I'm not aware of any analytical solution for it. However, I calculated it numerically using Wolfram alpha, and it gave me 0.393204. And here in principle, we are done with the answer, as the problem is asking us the fraction of the walkers that come back. But for completeness, let's try to find the probability of a particle ever coming back to its origin in 3D. This part is actually a bit tricky. Think of what can happen for a single walker. It might take a walk and then come back to its origin, and then it might do that again and come back to its origin. This could repeat x times, and after that, it could take a walk, but this time never come back to its origin up to infinity. So this should remind us of the geometric distribution. There we have consecutive coin flips, and we are interested in the mean number of flips to get a success, say heads with a probability of p. So in this case, we have something similar going on. We have repeated events of the walker coming back to its origin, and then at the end, we have the walker leaving the origin forever. So the probability of leaving forever is what terminates the consecutive quote-unquote coin flips in this case. Let's call that Q. To give an exact expression, the fraction of the walkers that do come back to its origin is going to be the sum from x is equal to 0 to infinity of x multiplied by p to the power of x multiplied by q. Here, q would be like p in the coin flipping scenario. So just like in the above, this mean is going to be 1 over q. However, we actually have to subtract 1 because we shouldn't count the final event where it wanders off to infinity. From here, q is equal to 1 over 1 plus mu, which gives 0.71777. Since q was the probability of never coming back, the probability that we want is 1 minus q, which gives 0.28223. This is an interesting and perhaps unexpected result, because the probability of the walker coming back to its origin in 1 and 2-dimensional cases was 100%. But in this 3-dimensional case, the probability of coming back to its origin is close to 28%. We call this a transient walker. To get an intuition of why, we can loosely say that in 1 and 2-dimensional cases, the space is restricted so that the walker doesn't have enough degrees of freedom to walk off to infinity. But it turns out that in the 3-dimensional case, that ability is unlocked due to the extra dimension. In fact, you can generalize the above solution to an arbitrary degree of dimensions, and what you will find is that the probability of coming back to origin keeps decreasing as the dimensionality increases. For example, I calculated the 4 and 5-dimensional cases, again numerically. For the 4-dimensional case, I'm getting the probability of return to be about 10%, and for the 5-dimensional case, the probability comes out to be slightly higher than 4%.